Hello students. In this video, we'll discuss the geometry of complex numbers. A complex number z, which is a plus ib, can be plotted in the complex plane by treating the real part of z, which is a, and we'll denote the real part of z, R-E-Z, as the x-axis component, and the imaginary part of z, b, which we'll denote as IMZ, as the y-axis component. So when I plot a complex number, I have the real axis and the imaginary axis. If this is a and this is b, this is where I will plot my complex number a plus ib. There are two important quantities that are associated with this complex number a plus ib. There is the modulus of z, which is the square root of a squared plus b squared, which is called the modulus. And there's the argument of z, which is the angle that this ray makes with respect to the real axis. So this angle over here, theta, is the argument of z. So for example, the complex number z, which is 1 plus I, has modulus z, which is the square root of the real part, which is 1 squared, plus the imaginary part, which is 1 squared, which gives me the square root of 2. And the argument of this complex number z is the inverse tangent of 1 over 1, the imaginary part over the real part. The inverse tangent of 1 is pi quarters. So we see that any complex number is uniquely determined by the distance it is away from the origin and the angle, exactly analogous to polar coordinates. Now let's see how we can represent this complex number with its modulus and its argument. This length over here is going to be the modulus of z times the sine of theta, and this length over here will be the modulus of z times the cosine of theta. Therefore, any z has the form modulus of z cosine of theta plus I modulus of z sine theta, and this is referred to as the polar form of a complex number. Now we come to the point where we use one of the most classical identities in complex variables, which is Euler's identity. And Euler's identity asserts that e to the I theta is cosine theta plus I sine theta. We can see how Euler's formula is deriven by using the Taylor series expansion for e to the x. I look at the expansion for e to the I theta, and I write this in its Taylor expansion as the sum n goes from 0 to infinity of I theta to the n over n factorial. And now I break the Taylor series into the even terms and the odd terms. This will be the sum. N goes from 0 to infinity of I theta to the 2n over 2n factorial. These are the even terms of my expansion. And I add in the odd terms. These terms are the odd terms in the expansion. Now, from the previous video, we know that even powers of I are either positive 1 or negative 1. And the odd powers of I are either positive or negative I. So I can simplify this as the sum, n goes from 0 to infinity, negative 1 to the n, theta to the 2n over 2n factorial, plus I, the sum, n goes from 0 to infinity, negative 1 to the n, theta to the 2n plus 1 over 2n plus 1 factorial. And now we observe that this is exactly the Taylor expansion for cosine of theta, and this is the Taylor expansion for sine of theta, and that allows us to conclude that Euler's formula is true. From this, we now see that any complex number z can be written in the form modulus of z, e to the I argument of z. And this form of a complex number will be useful when finding products and roots of complex numbers. Thank you very much.